All right, guys, let's get started. So usually I like to do a short review of what we did last time, at least, so that you remember what we did last time. But I was thinking about it. It's actually pretty useful for you guys to be able to give me a quick summary as well. So can anyone give me a quick, what was the take-home message from nearest neighbor search and from LSH? And try and condense it down. Yep.
Nearest neighbor search can be exponential in dimension?
Yep. Nearest neighbor search can be very challenging as a function of the dimension. It's a type problem which, when we first saw dimensionality reduction, it was to save an extra multiplicative factor of d. But really, for nearest neighbor search, that's where the savings are potentially much more drastic, because many of the schemes have something that's exponentially dependent on d. And what's LSH? Can someone remind me, refresh my memory? Someone else? Yep.
Locality-sensitive hashing, which takes advantage of the fact that two things that are closer collide with high probability than two things that are far away.
Exactly, right? So, the way that I would give a quick summary for this is exactly along these lines, is the main take-home from this was how to exploit collisions. This was very different from the types of ways that we reasoned about collisions before. So it was about how to exploit collisions. And the main take-home was that actually what we were able to get was we were able to get sublinear search time. Even though we had small space for some of the schemes that we discussed. So there was this row parameter that was really a property of how good your locality-sensitive hash function is at probabilistically distinguishing between things that are close and things that are far. And it's that same row parameter that shows up in actually this Indik Motwani scheme for getting better bounds for nearest neighbor search. So that's one of the main take-homes from that. And it's good exercise to try and ask yourself the same question so that you don't get too lost in the technical details. But now, today we're actually going to be starting something of a new topic. We're going to be talking about max flow. Now, how many people have seen max flow before? Yeah, so this is the annoying thing about, when you teach it at MIT, max flow gets covered in all sorts of different classes. Which classes did you guys see max flow in? 046. Anyone see it in anything else? 18200.
Moderate class.
Okay, yeah, that goes a little further. So max flow is one of those things which we're going to cover slightly different things eventually for max flow than you've seen before. But really, to make sure everyone's on the same page, this is going to be the standard intro to max flow, where I'm not going to assume anything for background, and we're going to build up some of the basic things for max flow. We might do it in a slightly different way than you've seen it before, and that's a good thing. But eventually what we're working up towards is that max flow is just one instance of much more general families of problems. So there are other things like min-cost flow, min-cost circulation, that are natural generalizations that generalize both max flow and shortest paths. They can have some interesting applications for doing things like matchings. We'll cover that. And then there are even much more advanced generalizations, things like multi-commodity flow. So we're going to redo some of max flow theory, but working towards some things that you hopefully haven't seen before. And that'll be over the next few lectures. So today, let's start with the standard max flow. So you guys don't get bored, flush out all of what you know about max flow so you sound surprised. So max flow doesn't equal min cut anymore, okay? I will hear gasps of shock when I say it. Darn, I ruined my punchline. All right, so let's start with the usual max flow problem. So let me just define it, and then we'll talk about where it actually comes from, and I'll ask for your guys' input about where you think it comes up. So max flow, as you guys have never seen before, you start off with a directed graph. Just to make things clear, I'm usually going to use the notation GVA, where A goes instead of E, where we usually talk about edge set, but here these will be called arcs because they're directed. So the important thing is that A is really ordered pairs. So X and Y can appear in the forward and backward direction. There's no problem with that. That's part of the constraints of the problem. This models whatever the underlying network is that we want to use to support some type of communication. What's also important is, how strong these different ties are. So this is contained within the capacity function, and we're going to use U to denote the capacity function. So it just maps the arcs to non-negative values. As a bit of foreshadowing, so the reason we're using U and not C here is because eventually we're going to be talking about flow problems with costs. So that's what C is going to play the role of. But for now, we have this capacity function that takes in an arc and tells us how strong the tie is between those two endpoints. And the only remaining thing to really specify the problem is that we have one special pair of vertices, the source S and the sink T. And the goal now, these are both vertices in the set V, so it's just that they're labeled as being special. And the important thing is now our entire goal is to try and send as much flow as possible from the source to the sink while violating what are the natural, without violating what are the natural constraints of the problem. So just so that we have a running example, at least in the first part, you can think about a graph that looks like this. So we've got our special source and sink, and now along each one of these edges we've got different capacities in here. We're not really going to study this example in too much detail, but I thought I'd at least draw something to show you what these things can look like and in general how you can write them. So these different values along the edges are just the annotations of what the different capacities are. So things can get a little confusing. I'll warn you that we have values on the edges which are both the capacities and sometimes the flows. So you always want to make sure you know which is which, but here I've written the capacities. Now the goal is to get as much, you can think of these capacities as being like the width of a pipe, or how much bandwidth is along a connection. So we want to send as much as possible flow from S to T. So let me be precise about what the goals of this problem are. And then the max flow problem will really be fully defined. So as I said, the informal goal is just to send as much flow as possible from S to T. Now the way that we can write this is I'm going to think about it as a maximization problem, where we can think about how much flow we're actually sending out of S. So this is the sum total of over all of the different arcs, so sum over all A, where SA is in the set of arcs, of the actual flow, this value F of S comma A, that we're sending on that arc, of how much is going out of S. Now there's a slight technicality, which is technically we could have arcs that actually go back into S, and we want to subtract out the flow that actually goes back into S, and we get this quantity, which sometimes, to make our notation simpler and allow me to not have to keep rewriting this, I'm going to note this as the size of F in this sense. This is called the value of the flow, right? Now we have some constraints because in order for it to actually be a physical flow, there are lots of things that you would hope that a flow actually does satisfy. So the constraints that we have on this function that maps arcs to the actual flow values on that arc are we have what's called conservation constraints. So here all it is that if I take any vertex V, and I'm going to suppress this notation that the sum will always be over just arcs. So if I sum over all the arcs where the arc goes from V to A, then I want that this minus the sum over all of the arcs in the other direction is actually equal to 0 for every vertex except for the source and the sink. So this is called conservation for a very intuitive reason. Why is this called conservation?
Flow in equals flow out.
Flow in equals flow out, right? So flow in, which is exactly what this quantity is flow out and this quantity is flow in, is just that the flow we're talking about is something physical where it can't disappear and reappear magically, except at the source and the sink. So you'll often hear me refer to this in shorthand as a conservation constraint. Now the only remaining constraint here is what's called capacity constraints. It's just that the flow that you actually send along an arc can never exceed what its capacity is. So we want this to be true for all possible arcs. So maximize the flow, subject to the constraint that you have conservation of flow and that you don't violate capacity constraints. So that's all the problem is. It's very natural. Now, what I thought I'd do is, usually when you give a lecture on max flow, you talk about all of the different applications of this problem. Let me outsource some of that to you. So what types of scenarios could you imagine trying to maximize a flow? What could this be used to model?
This is a quick question.
Yep.
So the flow is a function from A to
Yes.
E and
exactly.
R.
So the goal is to actually get as much flow, and flow will always be a function from A to something, well, non-negative, not necessarily strictly positive. And then you just have these constraints on what the flow actually is. But subject to these constraints, you actually want to maximize the total flow. So one thing, I guess, just as a quick diagnostic question, is you notice that in this formulation of the problem, T doesn't show up as something trying to maximize flow into T. So why doesn't T show up in the objective function?
Flow out of S equals flow into T.
Exactly. It's because, actually, the flow is conserved at every node except for the source and the sink. So this constraint is actually equivalent to trying to maximize the net flow into T. Those are the exact same problems, and that's why it doesn't show up. Okay? So now what I want to do is I want to outsource some of this question about, where does this come up? So what can you guys give me as examples? Real life scenarios where you could think about trying to maximize. Yep.
If you have a network like an internet.
Yep.
That situation.
Perfect. So computer network. And actually what's kind of tough is, I teach this sometimes when I do 18200, and then I recognize some familiar faces from there, so I know you guys know my jokes. So, my joke, at least when I usually talked about it, was you think of it as a computer network where the entire goal of the internet is to get you to stream Netflix as fast as possible. So you would be the sink, and the entire rest of the internet is set up as a way to try and maximize your frame rate quality. But, unfortunately, I can't reuse a lot of my old jokes, or if I do, you guys better still laugh at them. In any case, what are other examples where you can think of where, yep, in the back?
Suppose a bunch of people are in lobby 7 and they want to get to 2190.
Okay. All right, fair enough.
And no other people exist.
I see. Fair enough. And no other people exist, exactly. All right, so that's good. Or we could think about that more generally as just, transportation networks. Not all of which have a sync node of 2190. In fact, one of the original transportation networks this was applied for was the train system in Eastern Germany, because the goal was to actually figure out which railroads you should try and bomb to curtail the flow of Russian troops if they tried to invade. So that was actually the original application, and a lot of this came out of the Rand Corporation in the 50s. Are there any other examples anyone has? Yep?
Bipartite matching.
Bipartite matching. So let me make a distinction, absolutely. So the other thing is that what's so important about max flow is that it really does have many different applications, in the sense that many other problems that aren't naturally modeled as trying to send as much flow as possible from S to T, subject to these types of constraints, turn out to actually be things that you can rephrase in the language of max flow. So that's why some of the later generalizations that we'll talk about will become even more powerful, is because if you think about all of the applications max flow actually does have in something like combinatorial optimization, a lot of the generalizations like min-cost flow, multi-commodity flow, have a lot even richer family of generalizations and applications. But as you mentioned, for example, one of the canonical applications within combinatorial optimization of how to use algorithms for computing max flow is to do things like computing a maximum matching. We'll get to that later. Also to do things like scheduling. For example, there's some of these airline scheduling problems, and you can also think about partitioning problems in general, which come up in a lot of questions where you want to figure out how to lay out a graph to try and minimize how much the edges are stretched. So we're going to see some of these applications later, but now what I want to do is I want to talk about some first steps in understanding max flow. So now we're going to do this slightly differently than maybe some of you have seen, which is the first tool that we're actually going to introduce for reasoning about flow is something called the flow decomposition. So that's one convenient way to think about a flow as really being composed of some very simple types of atomic units. So this is a very good way to start reasoning about what flows can and can't do. So let me teach you a powerful tool for reasoning about flows. And what I'm going to assume, just because it makes the discussion a little bit simpler, it's not really necessary, I'm going to assume that no arc into S has flow, and the same for out of T. After all, our goal is to actually get as much flow out of S and as much flow into T. It's not hard to show that without loss generality you can always do that. But let's just restrict to the setting right now. So imagine we have no arcs into S and no arcs out of T, just for simplicity. And let me tell you the basic idea for flow decomposition. So here's what we want to show. Actually, have you guys seen flow decomposition before? So, okay, good. All right, so I picked a slightly different way to do this, which is, so the idea now is that we can take any ST flow. I don't care if it's max or not, but it needs to satisfy these two constraints. It needs to satisfy conservation and capacity constraints. Well, if you take any ST flow, then the point is that there's a way to decompose it into much simpler building blocks. So you can always decompose it into, well, in fact, you can always do it with at most M, which is the number of total arcs, ST paths, and cycles. So these are what I'll call the, these, if you think about them, are the world's simplest ST flows. If I were given a graph, forget about trying to find the max flow. One of the simplest things that I can do is I can take an ST path, and then I can just have some value for that path. Like in this case, if I went from S to 2 to 4 to T, that would be my ST path. And I could assign a value like 3 to it. And that would be something that would actually create a valid flow that satisfies conservation and that also satisfies the capacity constraints. Now there's something less obvious that I can do, which seems kind of silly, but you could do it, is you can also create cycles. So I guess here I don't have cycles, but one thing that I could do is, imagine I added a backwards edge here with some sort of capacity 3 along it. Then one thing that I can do is I can actually take some cycle in the graph and add something like 1 unit of flow along each one of those arcs. Now that actually is something which still satisfies conservation constraints because each node actually has net flow 0. It also does satisfy capacity constraints. It's just that you might think of it as a kind of useless object. Why? For this purpose?
You're not taking it out of S, you're not sending it.
Exactly. It's not actually accomplishing sending any flow from S to T, but it nevertheless is one of the basic building blocks which flows are composed of. So you can think about taking any ST flow that you want, and it's not true that you can decompose any ST flow just into ST paths, because there are things like cycles that really can't be decomposed further. But you always can take an ST flow, and you can decompose it into not too many different paths and cycles. So that's the basic idea. All right? So let's prove this. This will actually be, so when we prove the standard things about flows, things like min-cut, max flow, we're going to do it through path decompositions because this will be a very convenient way for reasoning about flows. So it'll be a slightly different take on some of the ways that you've seen it. So let's prove this. Are there any questions though first? All makes sense? All right, so the idea is we're going to do induction now. Any idea induction on what for the decomposition? Yep.
Number of non-zero edges in the flow.
Yes, exactly. Induction on the number of arcs with non-zero flow. So the basic idea behind this is instead of just taking a flow and immediately figuring out what its decomposition is into paths and cycles, all you want to do is make progress towards that. We want to find a way of actually pulling out either an ST path or a cycle in a way that when we remove that path or cycle, that we still get is an ST flow, but we've made progress in terms of the number of edges or arcs which have non-zero flow. So that's going to be the way that we do it. So what else can we do but consider an arbitrary arc with non-zero flow. So it's got flow greater than 0. And now what we're going to do is, so now what we're going to do is we're going to trace back from A and forwards from B. And this is the way that we're going to try and construct a path or a cycle. So I'm not telling you how exactly, what exactly is going to happen when we terminate. But we start off with this arc, and then we're tracing backwards from A and forwards out of B. So the basic idea, the basic first question is actually, what do I mean by trace backwards? So the basic idea here is that if we had our arc, which has some non-zero flow, then what I want to do is I want to find some other arc into A, which also has non-zero flow. And then I'm going to walk backwards along it. And the same way that I want to find some arc out of B that actually has non-zero flow and walk forward from that. So why should I be able to find such an arc? Conservation. Exactly, right? So the way that I'll write this, it's exactly because of conservation, is that because the flow on AD is positive, we know that the flow out of A plus, I just mean this syntactically, is that we can take these two facts that we know, the fact that there is flow out of A, that there's non-zero flow out of A, and the fact that we have conservation of flow, and together this implies that there must be some flow into A as well, and we take any arc which supports some of that flow into A. And the same thing works exactly for B, so that implies that we can always find an outgoing edge. Until what? So what types of conditions could we get into where we really couldn't trace backwards out of A anymore, or we couldn't trace forwards out of B anymore? Those are the two conditions. So now the idea is with just the symbol mechanism. So we trace backwards and forwards until we can reach a cycle. Now there are many ways that we could reach the cycle. Because, for example, one way is that in tracing back along A and tracing forward along B, those two things could meet. That's one way to actually create a cycle. And then the cycle actually involves this arc AB. But are there ways to create a cycle that don't involve this arc AB?
The lollipop. If you trace backwards from A, you could end up somewhere hitting somewhere in the middle of your own path.
Exactly. So what could happen here is I could create a cycle all by itself here. So therefore, I could create a cycle all by myself in B. So really, we need a broad definition of what it means to reach a cycle. So either one of these two things could either intersect each other, or they could intersect themselves. But the only other way that we can actually get stuck is actually if we reach both S and T. So now we're actually in great shape, because what we're going to do is we're going to let W be the arcs in the cycle or ST path, whichever we create. So in case 2 is the only case that we create the ST path. Now when we create the cycle, some of the edges that we explored might not be a part of the cycle. We just take whatever is that smallest cycle that we've created. And we let W be the arcs in the cycle or path. And we're going to let delta W just be the smallest flow value of any of these arcs. So the reason we care about this quantity is that now that we've found a cycle or path, it's something that we can subtract off from the flow. But we want to subtract off enough of it that we actually make progress towards our inductive assumption, which is we want to reduce the number of arcs with non-zero flow. So we better subtract off enough that some other edge becomes tight and actually goes down to 0. So now there's a very simple update, which is what we're going to do is we're going to decrease the flow on all the arcs in the cycle or path by delta of W. And the important thing is what we get is still a feasible ST flow, because the actual thing that we've taken off from it is going to ensure that we still maintain conservation. And then we're only reducing the flow, so we still satisfy capacity constraints. Now the important thing is that really one more arc really does become tight. So that's the entire point, is that we still get a valid ST flow, but the number of arcs with non-zero flow has actually strictly decreased. And that finishes our proof, right? So is there a question that I saw? Someone raise their hand? All right. So does this make sense? Too easy? Who thinks it's too easy? I can make things harder if you guys want. All right. Yep. Okay. All right, so let's use path decomposition now, flow decomposition, to actually do some interesting things. So we'll redo some of the things that you guys already know, but using the language of path decomposition. So let's prove, for example, okay, actually first let's do a quick diagnostic question before that. I'll ask you guys. So let's say we take some ST flow and we apply this flow decomposition to it. That's a very powerful thing to do in trying to understand flows. And we get out, as we just proved, is we get out ST paths plus cycles. Now, what if we ignore the cycles? What happens? What do we actually get out of that? Is it an ST flow? Mm-hmm. Yep. What about its flow value?
At least that much.
Stays the same, right? So that's the important thing, is that it tells you that things like flow decomposition tell you nice things, like if you actually have a max flow, you can assume without loss of generality that you don't actually need cycles to get to it. So you can always take a flow and remove the cycles in its decomposition and get another flow of exactly the same value, right? In fact, yeah, so I'll leave that. That's just that observation for the time being. But now let's apply flow decomposition. to prove something you guys have probably seen the proof of before. We have the notion of an ST cut, which is our basic way to try and upper bound the max flow. So an ST cut is just a set S of the vertices, but it has the constraint that the source actually needs to be in the set that we construct, and that the sink needs to be in the remainder of the vertices. It has to be outside of S. So the important thing about an ST cut is its capacity. So its capacity of this cut is just defined to be the sum of the capacities of the arcs that go only in the forward direction. So A needs to be in S, and B needs to be in V minus S. So all we're doing is we're creating some sort of partition of the vertices that necessarily contains S on one side and T on the other. And we're going to add up only the capacity of the forward edges. We don't even care about the backwards edges. And that's called the capacity of an ST cut. So one of the most basic things in the study of flows is just that the mid-cut, the capacity of the cut that you get for an ST cut is always a bound on the max flow. So you guys have, oh, was that the...
surprise.
That was the surprise, all right. Are you guys surprised?
Yeah.
All right, it's going to be too hard for you to pretend that you're surprised by this, but can anyone, so whoever's seen a proof of this fact before, that the min cut is an upper bound on the max flow, can you tell me something about how you guys proved it? Give me a little bit of reminder. Because you guys probably proved it in a slightly different way than we're going to prove now. Does anyone remember how something like that's proven? Yep.
You partition the set of nodes into two sets.
Yep.
And then show that that if S is in one set and T is in the other, then the flow across between one set and the other is at most the max flow, at least the max flow.
At most, it's cut at most.
Yeah. So very, very good. So the point is that what you do is once you have this partition, you give me any cut. Now the point is, flow is not conserved at S, but flow is conserved at every other vertex besides S and T. So the idea is that actually if you define the notion of flow in and flow out of some set in the obvious way, where you take all of the values of flows on arcs going out of the set and subtract out the flows on arcs coming in, that is actually equal to the flow out minus the flow in of S itself. Because everything else cancels when you actually do the sum. So a lot of times this is seen as just an algebraic trick, that it's a way to exploit conservation constraints to actually show that whatever the flow you've achieved for S is actually the flow out minus the flow in for the entire set. And then you only have so much units of capacity that actually go out of that set, and that's why it's an upper bound. So that's the usual proof. But what I claim is we can also see a different proof through something like flow decomposition. So can anyone give me an idea about how we can try and prove that the min cut is an upper bound on the max flow once we have something like flow decomposition?
I have a idea.
Yep.
So each ST path is going to have to cross the cut because it goes to T. And at that point, they use up some capacity from the cut.
Exactly. That's what our proof is. So that's exactly how the proof is going to go. I guess, yeah, let me erase this part. So already we're starting to get some gains out of this flow decomposition, because we have a slightly different proof of the usual min cut bounds the max flow. Actually, I find the proof a little bit more intuitive, so it depends on what your application is, but it's a pretty intuitive proof. Actually, both are, I guess. And the proof is exactly like you suggested. So remember, our lemma now is just that the max flow, where we maximize this quantity f subject to its constraints, is actually upper bounded by the min cut, where this min is now just the capacity of the cut S over all ST cuts X. And the proof of this, we get a very straightforward proof from the flow decomposition, is that we can take any flow and we can apply this decomposition to express it as ST paths and cycles. In fact, we can even ignore the cycles because, as we just discussed, actually removing the cycles preserves the fact that it's a valid ST flow, but doesn't actually change the value of the flow itself. So let's just care about the ST paths. And the entire point is just that each ST path has to cross the cut. Because somewhere, as it goes from S to T, it's actually going to traverse an arc that goes from one side to the other. Now, the entire point is that, how much a path gives us for the ST flow, there's actually a variable too, right? Because associated with each path is actually the value of the flow along that path that we pulled out. That's where we started off with this delta of W term, is when we found something like an ST path that told us how much we could pull out along that path. But the point is that every ST path that, let's say, if it contributes a value P to the ST flow, then it actually has to use up T units of capacity across the cut. So that's actually the end of the proof for the upper bound, right? Because, if we had the flow is too large, if it was larger than the min cut, then lo and behold, each one of these ST paths is going to consume more capacity than we have available crossing the cut to begin with. So this is actually one example of, what's really going on under the hood here is weak duality for LPs. So we're going to see this type of argument show up again and again, but in much fancier ways as we talk about generalizations of max flow, especially when we talk about things like multi-commodity flows, where we no longer have the property that min cut equals max flow, because for some of the things that we're going to study later, actually the cut version of the problem is NP hard and is even hard to approximate. But we're going to get much more powerful tools for actually getting a handle on, when we don't have exact equality, how we can prove approximate relations between them. So that's a little bit of foreshadowing about where we're going. So now that we have this statement that min cut bounds the max flow, so one of the first things we can do is we can try and get algorithms for computing the max flow. So you guys, I'm assuming, have all seen Ford-Fulkerson. What we're going to be doing in the next lecture, after we cover some of the basics of something like Ford-Fulkerson and give a slightly different take on it, what we're going to be doing is we're going to be studying ways to get even faster algorithms for computing the max flow. So Ford-Fulkerson is actually just one way of getting to the max flow. But what we'll really be interested in is, are there better algorithms we can design that actually make more progress each time? So we'll see towards the end of the lecture that Ford-Fulkerson really can have some problematic issues associated with it. So let me first define the first attempt for Ford-Fulkerson to try and get the max flow. So let's do attempt number 1 to use the idea of individual paths to try and get us to a max flow. All right, so here's what we're going to do is we need just a slight bit of notation. So W is a path. What we're going to do is we're going to let delta of W just be the amount of extra flow that we can push without actually violating the capacity constraints. So it's the min over the edges of the capacity minus the flow on that arc. So it's the residual. It's how much is left over that we could push beyond what we currently have. if there's any edge which has these two things equal, that edge is called saturated, and it means we actually can't push anything along that path. But now, our first attempt for max flow is pretty simple, is while there is an ST path, W, with delta of W greater than 0, then you can try and increase flow on each arc in W by exactly this bottleneck amount that we found. So I guess first question, just to make sure you guys are still paying attention. So how would I go about finding such an ST path? So not just any ST path, but one with delta of W strictly greater than 0. How would I go about finding that? Yep.
You can store an auxiliary graph that has this residual flow on it to compute shortest path or whatever else.
Yep, exactly. All I would do is I would remove all of the arcs in my graph that are currently saturated. And then by definition, whenever I find an ST path that only uses arcs that are not completely saturated, and then I really have found such a path if it exists. And if I did have such a path, for sure I could increase the flow in this way. By augmenting the values of the flows along these arcs, I really would get something with a strictly larger max flow. So right now, this is just an approach of, given something that may or may not be a max flow, looking for a simple procedure to try and increase the flow value. But there's a big problem. There's a reason why it's attempt number 1. Anyone tell me what the problem could be? So should this work? No. Definitely not, right? So what's the problem? What could go wrong and what does go wrong with such an approach?
If the early paths are, unlucky, we might have everything be blocked, but still have more be possible to a different system that doesn't involve those initial paths.
Exactly. So the biggest issue is what always happens with algorithm design and can get you wrong, is that you're doing a step that, if you could do it, makes progress, but you always have to worry about, are you painting yourself into a corner? So that happens in much more serious ways for other problems where really there isn't a way to get you out of that corner once you've painted yourself in. But this is something which even this attempt really does get you stuck in a corner for a reason that's pretty intuitive. So let me give you a simple example of what can go wrong, and then we'll fix it, and then I'll introduce the notion of a residual graph. So the big issue here is that we could easily have some simple examples that look like the following. So imagine we had this instance of our max flow problem, and all the arcs were capacity 1. So what's a way that if I chose, we know the max flow is 2, but what's one augmenting path I could choose that would really paint myself into a corner?
Up, down, and then up again.
Exactly. As soon as I do this, then I'm completely dead. Why would you ever do that? But sometimes algorithms are dumb, and they could do this. And then you'd be stuck, because even though the max flow really is 2, the only way to get to it is actually trying to undo the flow along this edge. So this is where you really need the second attempt to try and do this, is just the notion of the residual. So this is what motivates the residual. Because the way that we constructed this graph, this auxiliary graph that we use to answer questions like this, was we took our original graph and we just pruned out all the edges that are saturated. But that's not the answer to everything that we can do, because even edges that are saturated, they really have created reverse links in the opposite direction because of flow that we can undo. So let me define the residual graph. We're going to use this many times. So the residual graph so we're given some instance of the problem with some capacities, and we're given some ST flow F, and all we're going to do is we're going to perform the following operation. So every time we have an arc in G, which goes between some pair, A and B, and we have some capacity, UAB, on it, well, that's going to be transformed into one or more arcs in both different directions. So the value of the forward arc is just UAB minus the flow. So this is how much left we can push in the direction we've already been pushing. But there's still the issue about how much we can undo that we've already pushed. So that's just FAB, so we actually get an arc in the reverse direction. And all we do to construct the residual graph is we take our graph, we take our flow, and then we just use this simple table to go from every arc in G to one or more arcs in H. And if some arc has capacity 0, I'm just going to delete it because it's irrelevant anyways. So if we had a saturated link, it would just go to one edge backwards, and that's it. So now we have our second attempt for max flow, which, surprise, surprise, is going to work. So max flow attempt number 2, and this is the most naive scheme for trying to compute a max flow, but we're going to see fancier things. So I'm going to let delta sub h now be the min on some path over all of the different arcs of the capacity of that arc, where this is now the capacity in H, in this new residual graph. And our approach is just a slight variant, so all we're going to do is, well, there exists some ST path, W, in H, which, delta H, greater than 0, all you're going to do is augment along it. And by how much? By delta H of W. So what I mean by augment here is that that really is some path in the residual. So every edge that you're using the residual has one of two meanings. What could the meanings of augmenting along an edge in the residual be? What are the two things it could map to in the original path? So if, for example, it was some arc that was not fully saturated, right? So we had some capacity UAB, and then the flow wasn't fully using up that capacity. That could be one source of the arc. So when we have that arc in the residual and we want to use it, that just corresponds to pushing more along the edge. But by the flip side, we could actually be using an arc in the reverse direction, which would actually correspond to decrementing the flow that we already have, right? So those are the two meanings of augment, is it depends on where the edge in the residual came from, whether or not augmentation means pushing more of the flow in the direction you already are pushing, or it just means pushing less in the direction you've already been pushing. So are there any questions about this? Does this algorithm make sense? Everyone on the same page? All right, so now let's do something a little bit different with it, which is, does this algorithm always work? Yep.
You can have infinite loops. No?
I can have infinite loops? What do you mean by that?
So, like in the example, if you can add in the path that you showed, and then like add in the opposite one, and then you can iterate over adding the same flow again and again.
Oh, right. But see, the flow here, the ST path still is an ST path. So what I claim is that when you actually do an iteration of this algorithm, that you're actually strictly increasing the actual ST flow of whatever flow you've created. So when I push, when I augment along delta H of W, when I augment along W by this amount, well, what augmentation means depends on where the arcs came from, whether they were forward or undoing flow. But regardless, whatever that change is, actually strictly does increase the ST flow value of the thing we've created so far by exactly delta H of W. Yep.
Are we assuming that the capacities are all like integers or something?
There's some reveals.
So that's a good question. So let me actually take a vote first, because now maybe we can get to something a little bit more surprising. Does this algorithm always find the max flow? Yes.
With what?
I'm not going to say.
I know.
With arbitrary capacities.
With arbitrary time?
Yeah, with arbitrary time. Yes.
Arbitrary finite time?
Finite time.
It's not going to matter. But all right, so arbitrary capacities does this if you want to get epsilon close to the max flow, right? Does it find it in a finite number of steps for any fixed epsilon?
Yes.
Sure.
Who's willing to wager?
Wait, for any fixed number of steps? Wait, what?
No.
So the question is, if I have arbitrary capacities along the edges, is it true that, let's say, I give you a graph and I want you to get within epsilon of the max flow. Epsilon is 1 over 100. Does it get you to within an additive 1 over 100 of the right answer in a finite number of steps? I see a lot of yeses.
Yeah. Maybe not.
Just because I'm leading you to say no?
No, because when we're using arbitrary reals, we could be making very small improvements that are like decreasing improvements.
Yeah.
Ooh.
Never actually get close to the
Yeah, that sounds a bit tricky. I mean, once I'm probably going to ask you something that sounds tricky, but actually is the correct intuitive answer, and I'll just be messing with you. But this time I'm not. But I'm a little worried about that. So is anyone else worried about that?
Yeah.
Yes.
A way to think about a counterexample is just like have like one graph from S to T up here and a completely separate one down here. And the algorithm could just add things to the top and never touch the bottom. And then you would like...
But even in that example, the top graph would already be a counterexample.
Well, if you want epsilon, right? Say like the best flow from the top is like F and the best flow from the bottom is also F. But like you only operate on the top, then you will approach F. So you only look at like half the curve.
I think the top one would still be a counterexample, but let's think about that, because even then the total flow, the max flow would be 2F.
Yeah.
And then actually, even if the top one, if you could keep doing operations, which were all strictly increasing the flow, it would still get you into trouble. But let me give you another example. That's true. That's fair. So this one we're not going to work out all the details for, but this is exactly why I like redoing. I don't want to assume what you do and don't know for max flow because of things like this. So actually, this is a big technicality that you do have to worry about, at least otherwise you'd be making false claims. So let's take the following graph. And we're going to have 3 special edges down here. Which the capacities of these edges that I'm going to create are 1, R, which is root 5 minus 1 over 2. Why wouldn't it be? And everything else is going to be some integer, which let's say it's strictly larger than 2. Okay? So now, exactly as you mentioned, there's this issue that, see, if you only had integer capacities, the fact that Ford-Fulkerson works is immediate, because you have a bound on every time you execute this step, you're actually making noticeable progress. Whenever you subtract out things, you started with integers, so you're never going to get something except for integers. And every time you can augment, you can increase by at least 1. So you have a lower bound that started off with 0 flow. You have an upper bound, which is something naive like the total weight of the edges going out of S. That's an upper bound for how many times you could execute that. And lo and behold, you'd be able to show then that that thing really does work. Same thing works, for example, for rationals, because you could just clear the denominators and do the same argument. But as soon as you have issues like this, when you have reals, you can actually be getting such small increments that you're never actually making all the way of the progress you want to get to. So this is a big issue, is that max flow is not just about integer capacity instances. When you have reals, this complication comes, to bear full on. So here, what I claim is that the flow, so let's see what the max flow is. So I claim the max flow of this instance is actually 2m plus 1. So can anyone prove that for me?
Can you just do a min cut?
Yep. This way, m, and 1, right? And it's clearly an upper bound because I could just cut all of these edges and then I get 2m plus 1. But actually what's going to happen is that if you implement Ford-Fulkerson badly, if you really try and do something pathological in the order that you do these updates, then what you're going to get for the particular choice of which paths to augment on, it actually converges to 1 plus 2 sum of Ri from 1 to infinity, which is actually 3 plus 2R, and is strictly less than what the max flow is. So you get stuck and mired in all these small little updates that, each time you run through the sequence of operations, what you're really getting is some diminishing value of R, power of R in there, and you never actually make it all the way to what the max flow actually is. So even though you're making progress each time, you don't get all the way there.
Yeah.
So let me tell you, you can work through the actual details, but let me tell you essentially how it works. So you're going to do some alternation between the different paths that you're going to augment along. And we'll keep track of the residual capacities of these different edges as we're going along. And the different paths that we're going to use, first thing we're going to do is we're going to send some simple flow from s to 2 to 3 to t, which we're going to send 1 unit of flow. So it goes all the way along here, and that's fine. And what's going to happen to the new capacities of these edges, we get 1r and 0, because this edge E3 in the middle is now completely wiped out. But the magic happens now, which is that what we're going to do is we're going to do P1, which will be, I'll tell you what it is. So it's S to 4 to 3 to 2 to 1 to T. So now that you actually have this edge going in the reverse direction, because it's in the residual graph, because it was saturated, you're going to go all the way along here. But the issue is that now your bottleneck is actually not 1 anymore, because you're actually using this edge. Your bottleneck is actually going to be R. So the amount of flow that you can actually send here is going to be R. And what's going to end up happening is you're going to end up getting R squared times 0 times R. And the same way there are a few other paths that you can end up just repeating this example. And you're going to end up with diminishing powers of R that you're actually increasing along. So this is a big complication. So some of the stuff that we're going to study beyond Ford-Fulkerson are things like when you're given even things like rational capacities. They don't have this issue that they never terminate, but they have this issue that if you weren't smart about how you choose the actual flow paths, you could end up making very, very little progress. So can anyone give me an example, for rationals? Let's say we want to create a flow network with all rational values, or even integer values. If we have really wide ranges, dynamic ranges for what those integer values are, how could we create something that takes a long time to actually find the max flow? Does anyone have any intuition about this? Yeah?
You can use that graph and set the top and bottom to have lots of capacity and very, very low capacity.
So what I can do is I can take some really large power of 2. And here, we know exactly what the max flow is. It's 2 to the L plus 1. But what can keep happening is you can keep thrashing on these different paths. So the first time you might choose a bad path here, which actually uses this 1, and that ends up becoming the bottleneck. So you're only augmenting 1 unit flow and making 1 unit progress. And yet then the next time, all you're allowed to do is, then if you really chose the wrong path, you could end up undoing that flow and adding 1 more unit, and you can keep thrashing in this way, right? So if you're very naive about how you choose your ST paths in the residual graph, you can have a really bad time because this algorithm would take time exponential in L, right? So this is what's called the notion of like strongly polynomial time versus weakly polynomial time, is that algorithm would run in polynomial time. The polynomial there depends on what the largest integer is. So if you have something like 2 to the L, it would run in 2 to the L time. So actually getting things which don't have that kind of dependence takes a little bit more work. That's something that we're going to see a little bit later on. Does anyone have any heuristics or ideas about how to try and avoid these sorts of problematic cases? How would I not get trapped in things like this? Yeah, sure.
What if we just choose the largest delta of any ST path?
Yep. So that's one good way to do things, is to actually choose whichever path we can augment the most along. There are lots of other approaches that you can do, like you can look for the shortest path in terms of graph theoretic distance. That also is something with slightly different guarantees. There are also tricks that we're going to get into next lecture called scaling. So one strategy is just to, if you think about a problem like this, there are some really big values out there. So what if you only focus on the big values? You took all of the edges whose capacity is at least 2 to the L. Then you'd just be ignoring this one edge in the middle, and you'd find your max flow really, really quickly. So you can think about building up better max flow algorithms by slowly rotating in less and less significant bits and figuring out how to update your flow based on the new bits that become available. So that's called scaling, so we'll cover that next time. Now let me first tell you a little bit more from Ford Fulkerson. So let me give you some equivalent conditions for thinking about when a flow is maximum. And that'll be the last thing that we cover in this sort of introductory lecture on max flow. So what I claim is the following, right? So if we took that approach of looking for ST paths in the residual, then we can ask the question, when, what if there is no ST path in the residual? This is already assuming away some of the issues, right? Because the original algorithm we had, where we kept augmenting along paths in the residual, we had this issue that we don't know we ever terminate. We could be making just vanishing progress and never actually reach the end of that while loop. But here we're assuming away that issue because we're saying, what if we got to the point where that algorithm actually can't do anything anymore, even if it's just barely increasing the max flow? So the point is that the claim is that now we can construct our cut as we're just going to let S be the nodes that are reachable in the residual H from the source S. And what I claim is that the following two conditions hold, from which we're going to build out some nice if and only if conditions about max flow. So what I claim is every arc AB, which goes from S to the complement, is actually saturated. So it has its flow equal to the capacity of that arc. So why should that be the case? If we took this Ford Fulkerson algorithm and we got to the end, where we can't find any path in the residual from S to T, and we define the set capital S now as all the things that the residual can still be reached by S, why is it true that at the end we really do have this condition that now every arc that crosses from S to S bar is completely saturated and we've pushed as much as we possibly can? Yep?
The only way for there not to be an edge from A to B and H is if it's saturated.
Exactly, right? And the reason for this is just else AB would be in this residual graph because there would be something left to push along it. So it would be in the residual. So the only remaining thing that we actually have to prove to be able to get some other nice equivalent versions of max flow is that what I claim is that the reverse arcs are also in good shape because every arc, BA, with the same conditions that A is in S and B is in B minus S, what I claim is that it has f of BA equal to 0. So why is this? Equally easy. Too easy? Yep.
Otherwise, A to B would be in the graph because there would be a reverse flow.
Exactly. Otherwise, the arc actually would be in the residual. Because if we had any flow from B to A, then that would be some flow that we could undo and would actually correspond to taking an edge in the residual from A to B because we're undoing that flow. So this is great because now we can actually build out our equivalent definitions of max flow just from the fact that if we reach this condition, we're terminated, and we can't find an ST path in the residual, we know that we have these two conditions are actually met. So let me give you some equivalent ways to think about max flow. Your TAs clearly finished their homework on time. Conditions are met at termination. Well, what I claim is that we can now draw some strong conclusions, because if we take capacity of this cut, well, I claim that, so first of all, the capacity of this cut is actually equal to, just by definition, the values along all the different edges going forward, which are now the same as the capacities, right? Because at termination, for any of these edges which is going forward, we know that the flow is equal to the capacity of that edge. So I've just replaced U of AB with F of AB, same thing, right? Because of condition 1. In fact, I can do something else, which is I can even subtract off all of the flow in the reverse direction. Why? Because it's 0, right? So that's great. And now what I claim is, this fact, the standard proof that you have of, weak duality, the fact that the min cut bounds the max flow, is exactly the thing which tells you that this quantity right here is actually equal to the value of the flow. That's because you have conservation of flow in everything except for S. So if you were to take the entire set, capital S, and look at the flow out minus the flow in, that's nothing more than the same as the flow out of the source minus the flow into the source. So now we actually have this nice equivalent thing, and now what I claim is that the following conditions are all different ways to state that a flow is maximum. And this will be very useful in some of the discussion we do later. So F is a max flow. That's a thing that we want to create equivalent conditions for. Well, there is no ST path in H, so in the residual, with delta H of W strictly greater than 0. That's one equivalent, completely equivalent way. And the other way is just that we are given some flow whose value is actually equal to the capacity of some ST cut. So this is one of the main takeaways, is that these are all equivalent ways to think about what a max flow is. So for example, why can we go from 3 to 1? So why does 3 imply 1? Someone help me out?
All of the cuts are apples to apples.
Exactly, right? So Exactly. So I claim now we actually have all of the tools in place to prove these conditions are equivalent. So 3 to 1 is easy. Why? Because it follows just from the fact that max flow is upper bounded by min cut. The thing that this time we proved through flow decomposition, just using the fact that a flow is a sum of these primitive objects, which are themselves ST paths and cycles, and that every ST path has to cross the cut at least once, so it charges whatever its value is of flow along it. So that's simple. I claim another way to think about an implication of this chain is that something else that's easy to prove is that not 2 implies not 1. So can anyone tell me why that is? Just using tools we've done?
If there exists an ST path, you can augment the flow and get a larger flow.
Yeah, exactly, right? This is just what was the workhorse under Fort Fulkerson, is that if there is an ST path in the residual, well, and that delta H of W is strictly greater than 0, then there is some amount that we can actually increase by. We do have all these other complications that I mentioned here that, if you really care about the termination of the algorithm, then you might be worried that you're augmenting by so little that as you keep augmenting by less and less, you converge to something that is not the max flow. But in any case, we already know this implication that not 2 implies not 1. So that's the same thing as, 1 implies 2, which is getting our chain going. So the only other thing that we need to prove is that 2 implies 3. And this is also pretty straightforward, right? Is that once we found that, so can anyone tell me why 2 implies 3? The answer is somewhere above it.
We constructed the guy.
1.5 points.
We constructed it, right? This was the proof of 2 implies 3. Because when we have no ST path in H, that's where we defined what S was. And that's how we actually got whatever the set was that minimizes it. Was that we found that set S, and then we just showed that it has these properties 1 and 2, which we exploited to change the fact that capacity is defined with U here. We changed that to F because of property 1. And then by property 2, all these guys are 0, so we put that inside. And that's exactly the same thing as the value of the flow. So this proves all the equivalent versions of max flow that we get from this. So a lot of times we're going to move seamlessly back and forth between these different versions of what it means for a flow to be max. And actually we're going to see versions of this come up in different types of problems. So one of the things that I think will be a lot of fun to study is later on we're going to study the min-cost flow problem and min-cost perfect matching. And when we work towards getting understandings of equivalent ways of thinking about what is a min-cost flow, what makes it be the right answer, we're actually going to get some fun interpretations through economics and through market clearing, just by interpreting what those conditions are. So really where we're headed is that max flow is something many of you guys may have seen before, but we want to build out from this theory. We want to get more efficient algorithms based on scaling. We want to build out from this theory and cover other generalizations like min-cost flow and also multi-commodity flow. And that will be an entirely different beast. So more stuff next time, so see you next week. We've got p-sets here.